is here. Just need 3 more. Said I need 3 more, and nobody showed up. Is this all we get? Oh, there's one. All right. There's one more here. Okay, I'll take it. Good afternoon, everybody. Hello. We've got very straightforward agenda for today. Video, short and sweet. Oh, Zeph is here too. Clock in there. There we go. Short and sweet. I've got answers for the last problem set, and then we'll review today's problem set, and you'll spend the rest of the time working on that. That's all there is to it. And then Friday we go back to the game of chess. So, but meanwhile we have these awesome problems dealing with angles and polygons and circles, right? All the good stuff, right? The meat and potatoes of geometry, all the shapes. Okay, so go ahead and take out your problem set, which should have been turned in before this morning, and compare your answers to mine. I'll go over where and when things can be different, what should be the same. So for the first one, we are finding all of the triangles with the particular features to which out of this bunch, where are the isosceles, the equilateral, scalene, right, obtuse, and so on. Okay, so here they are. Notice GHI, the equilateral triangle, is also here on the isosceles list. Every equilateral triangle is also isosceles. The naming convention, you need to have triangle in front of the name, okay, because triangle, DEF, is not the same thing as angle DEF, okay? One is the whole shape, one is just referring to this bit right here, okay? So make sure you put the triangle in front so we know which 3-letter object you're referring to. Angles, the order does matter. You need to make sure the vertex is in the middle. With triangles, all of them are vertices, so the order does not matter. You can have triangle DEF, you can have EFD, you can have FED, FDE, right? This way, that way, I don't care. It doesn't matter. Makes no difference in a triangle. And Eileen's iPhone is here. Excellent. I hope it brought the rest of her with it. I'm going to assume as such. Okay. Second batch, very much like the first. Here are the scalene isosceles, right equiangular, and obtuse. All the equiangulars are also equilateral and vice versa, so both of those get thrown on that list. But there are no obtuse triangles here. Okay, they did ask for which triangles, so yes, you need all of them. All right, moving on. Number 5 has you building triangles out of toothpicks now. We've been using toothpicks an awful lot, it seems. You could almost, I'm wondering if I could like make the whole year like geometry, toothpick-based geometry. Just have that be the entire class, all toothpicks all the time. I'm sure it could be done. Might be fun. Anyways, we're just making a triangle right now. So out of exactly 20 toothpicks, how many different isosceles triangles can you make? Answer is 4. Here they are. You can have it 2, 9, and 9 to a side, 4, 8, 8, 6, 7, 7, 8, 6, 6, 7, 5, 3, 0, 9. How many scalene? Another 4. 3, 8, 9, a 4, 7, 9, a 5, 6, 9, and a 5, 7, 8. How the 3, 5, that's number of toothpicks per side. Okay, so a 2, 9, 9 is a triangle that has 2 toothpicks and then 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Probably shouldn't be quite as slanty as that, but you get the idea. I love this problem because there's so many ways to go about this. You could get actual toothpicks and work this out and play around with them to see what kind of triangles you could make. Or you could just draw it, like I've done here, and keep making sketches to work out what combinations are possible. Or you could do it entirely mathematically, right? Just looking at the numbers. I know I need to have 2 sides that match and a third side that stands alone. Of course, there's no possible way to make it equilateral because 20 toothpicks does not divide evenly into 3. So you know that'll never be different. So you could set this up as variables. Just call this side x, y, and y. And x plus y has to equal 20. And find every possible solution to that equation. Okay. Or you could look for a pattern. Once you've found one, say, hey, I've got this guy. What if, in order to keep these the same, if I take a toothpick off of here and put it there, right, off of each one, these both get 1 smaller, and this gets 2 bigger each time. That's what's happening in order here as you go. All right. And numbers for Carla, does that explain what you were looking for? Yes, okay. Okay, number 7 then. Here we have a grid. It's called a square lattice. It's a grid of dots, okay? That's all we're talking about. And what we want to know is how many possible triangles can you draw so that segment AB is still one side of your triangle. So you could draw that one, or you could draw here, you could draw to there, you could draw to there. Basically, you're going to connect to all of these dots in order. So you could draw all of them and count up how many triangles, or realize, hey, every time I'm connecting to one of these other dots in the grid, how many other dots are there? Well, it's a 5 by 5 grid, so there's 25 dots to choose from. Some of them are already taken. I can't connect back to A or B itself, right, just on top of it, or the one in the middle, or even the ones over here. I'll still end up with just a straight segment, right? That's not a triangle. That's no good. So those 5 are no good. So I subtract 5 and I get 20. Okay? And we probably will have to actually draw some of them to at least get a feel for which dots, which rows or columns, or maybe a diagonal, everything, to find out which ones can be isosceles, which ones can be right, which ones can be acute. And obtuse, you could find it the same way as acute and right, but I would recommend, by that point, everything has to be either right, acute, or obtuse. So if you found all the rights and the acutes, just subtract from the total to leftovers must be obtuse. Okay. There's that one. And finally, we have this guy, which is like Geometry I Spy. I kind of like this one. This is definitely a fun problem to do. So you have this ginormous picture with all these lines intersecting, and all you had to do was find the following inside it. And here I have all the possible options. You only needed one of each, so one rectangle that's not a square. Okay, so either of those could work. And you can name these in many different ways. It doesn't have to be ADPK. You're just looking at this rectangle. Okay? So you could call it DPKA, you could call it PKAD, doesn't matter where you start. You could go the other direction, DAKP, AKPD. Okay? Any of those would work. As long as you have those 4 letters and you're moving around the outside in order. Please do not go A, D, K, P. I'm not connecting D to K. Okay? Don't go along the diagonals, you go around the outside. Okay? So as long as you meet those criteria, you have an effective name for a quadrilateral. Notice at this point for quadrilaterals and then pentagons and hexagons and on up, we don't put a special symbol in front of them. There's nothing else you can make out of 4 letters. It's going to be a quadrilateral. Okay, so I don't need the triangle versus angle specification there. All right, so there's all of your options. I'll give you a minute to read through those. Again, you only need 1 from the list. Okay, with that, what questions do you have on the level 1 problems? None? All right, then let's go to level 2. Level 2 continues with the toothpick triangle problem, except this time we have 24 toothpicks to work with. How does this change things? Right, that's that step 4 of always reflecting on what could have been different. Well, if I had had 24 toothpicks now, we've been talking, because I would have been able to make an equilateral triangle. 24 is divisible by 3. Here it is. You can get 1 of those. But now we can make 5 isosceles triangles and 7 different scalene triangles. And once again, the equilateral triangle is also isosceles. Same techniques as before. Number 8, another lattice. This time my AB segment is at a slant here. So that means I actually get more possible triangles out of this because no longer do I have to worry about landing in line with AB. There's no other dots along that line. I just can't hit A and B themselves. But every other point here is valid. There are now 6 times 5, 30 points. Minus those 2 gives me 28 possible triangles. 8 isosceles, 5 right, 8 acutes, subtract to find 15 leftover obtuses. Questions on level 2? All right, level 3 then had 2 problems very similar to each other. We want to find out how, if possible, these 2 could intersect in the exact number of points. So here they are, square and circle intersecting at 1 point. Very easy to do right there, and that's not the only way to do it. It doesn't have to be the corner. You could have it at any other corner. You could have it right on the side and make it tangent to, and then it could be anywhere along either side. Okay. 2 points, gotta go inside like this. And then if you push them closer together, you can get up to 3 points so that the square goes in the circle, hits the other side, and comes back out. 1, 2, 3 there. And for 4 points, it is important that your square and circle be the exact size they gave us to begin with. Otherwise, this would not work. So either you make sure they are the right size, or in forcing 4 points of contact, you end up with the correct size in order for the circle to fit nicely inside the square. 1, 2, 3, 4 dots right there. And then the second one is similar, but with a circle and triangle. We are now going for 1 point of contact, 2 points of contact, 3 points of contact. Now the circle goes in the triangle, crosses, hits the backside, comes back out. And D, once again, the sizing is important to get 6 intersections here. If your circle were too small, you could fit inside here and have 3 points there. If your circle were too big, you'd go right around and circumscribe the triangle, and you'd have 1, 2, 3 points right there. Of course, it could be even bigger, and then you'd have fewer than that. But we're right in between, so we can squeeze it and get a 1, 2, 3, 4, 5, 6 points, 2 at each corner. All right, last call for questions from this problem set. Okay, seeing and hearing none, let's take a peek at today's work. Problem set 2 from this section focuses on symmetry. All of these symmetry questions. So we have folding a sheet of paper, okay, and then like cutting out pieces. So classic paper snowflake process here. If you have some scrap paper, go for it. Try it out, physicalize it yourself. Otherwise, practice your mental imaging and visual processing, spatial reasoning skills. See what you can do without an actual piece of paper. And if you take a look at this example, you'll know why I had to include this problem at some point, right? 27, 28, 29, 30 deals with rectangle, rhombus, isosceles trapezoid, and isosceles triangle, respectively, finding all of the symmetries in these basic shapes. So this is just a good baseline exercise. And then 34 is where we start applying it to more interesting scenarios. Here we have a bunch of different gemstone cuts. Okay? Not just diamond, but these cuts apply to any type of gemstone. Different ways you can shape it, mold it to make pretty shiny rocks, okay? They're a big deal. It's a major industry. And notice you might be thrown off here, like, what? Why would they call this the princess? I don't know. They come up with these names. This one's called emerald. Okay, so emerald is both the type of stone, which is usually green, as well as a cut of stone. So you can have an emerald. And yes, this means the Chaos Emeralds from Sonic are the wrong shape. It was so easy, but you know, they screwed it up. What are you going to do? Okay. So here we're just examining, you know, these fun shapes that appear in real life and finding what's symmetrical about them. Okay. Useful to know, okay, just to like be vaguely familiar with and recognize that, you know, these are possible. Maybe you don't go to jewelry stores. Maybe some of you have looked at jewelry. Girls, do you have a bunch of jewelry? Do you like going shopping, wishing that, I wish somebody would give me one of these? Right? Guys, you got to get to know this stuff because one day you're going to want wives or girlfriends, and you buy them jewelry, okay? That's how it works nowadays. So you need to be familiar so you know what you're getting yourself into, okay? Girls, you got to know so you know what you like so you can direct and hint at and wink wink and you don't drop those subtle nudges of what he should be getting you, and also so you know if he's trying to cheap you, okay? Cheap out on you? That's the phrase, cheap out on you. Yeah, right? Anyways, okay, some life knowledge there. Know your gemstones. Anyways, that's level 1. Level 2 is more. It's just more of the same. So we got more paper folding symmetry. We've got some more standard shapes symmetry. This one, another application, this time 2 different bingo card arrangements, okay? Getting 5 in a row is so boring. Let's see what other fun shapes we can fill in our little 5x5 grid there. These are cool, right? Reminds me of the old, old first-gen pixel graphics on video games, right? Little Space Invaders and Centipede kind of things. Anyway, so that's a neat one there. And then level 3, another paper, symmetry, and more find the symmetry on everyday things. This one, the dice faces, 6-sided die. And quilt blocks, once again, just like the example from the text itself. Okay. So there you have it. Any immediate questions or concerns at this point? No? All right, then give that a go. Totally crush it. I will put the music back on, wrap up the YouTube video, and be on standby. If you do run into any questions, feel free to ask. But for now, you're on your own.